Imagine you are standing inside a city of 5,000 people, a city that has not touched land in 93 days, a city that has not received a single delivery in 6 weeks, a city that is currently moving at 30 knots through water that, if entered, would kill you in under 20 minutes. There is no supply chain. There is no resupply convoy approaching from behind the horizon. There is no municipal water authority, no regional power grid, no hospital system connected to anything beyond its own walls, and yet inside this city, surgeons are operating. Bakers are producing 3,000 loaves of bread before dawn. Laundry machines are cycling. Jet fuel is being moved through pipes embedded in the hull. Air is being conditioned. Sewage is being processed. Fuel oil is being burned at a rate that would make a mid-sized power plant blink, and the reactors, in the nuclear variants, are sustaining criticality without a single technician from the outside world checking a single valve. The question that the title of this video places in front of you is not dramatic, it is an engineering question. How does this city know what it will need before it needs it? How does it prevent shortages that, in this environment, carry no recovery option whatsoever? Because out here, if the water desalination system produces below threshold for 48 hours, you do not call the utility company. You manage a crew of 5,000 increasingly dehydrated people inside a steel hull in hostile waters, and you do it with whatever you have already stored, already engineered, already anticipated. This is the system. This is how it works. And understanding it means understanding a philosophy of logistics that civilian infrastructure has never been forced to develop, because civilian infrastructure has always had somewhere to call. Start with water, because water is where the mathematics of survival become impossible to ignore. A Nimitz-class carrier consumes approximately 400,000 gallons of fresh water every single day. That number contains everything: drinking, cooking, showering, laundry, medical sterilization, machinery cooling, aviation fluid systems, boiler feed water for the catapult steam systems. 400,000 gallons every day from an ocean that contains not one drinkable drop by default. If you lived here, if you woke up in a rack that is 22 inches wide and shared your sleeping compartment with 89 other people, you would be entirely dependent on a system you will never see, located in spaces below the waterline, running 24 hours a day without interruption. The system is evaporative distillation combined with reverse osmosis, and it is not a backup system or an emergency measure. It is the only source. Seawater enters through intake valves, passes through multi-stage flash evaporation units that heat it until the freshwater fraction vaporizes and separates from the salt, condenses on cooled surfaces, and is collected in storage tanks before being distributed throughout the ship via a pressurized network of pipes that runs through every deck. The reverse osmosis units handle secondary load, high-pressure membranes forcing seawater through barriers so fine that salt ions cannot pass. Together, these systems must produce enough water daily that the tanks never fall below a calculated safety margin, because the safety margin is the only buffer between operational normalcy and a crisis that cascades through every function simultaneously. Here is what most people never consider. The failure mode of a water shortfall on a carrier is not thirst in isolation. When water pressure drops below threshold, medical operations become impossible. Wound irrigation fails. Surgical field sterilization fails. Aviation maintenance requires water-based coolants in several aircraft systems. Food service ceases. Personal hygiene deteriorates at a rate that, within 72 hours in close quarters, begins creating secondary health cascades that the medical department must now manage on reduced water. One system's failure does not stay contained. It propagates. The engineers who designed the water architecture understood this, which is why the systems are redundant, not once but multiple times, why maintenance windows are staggered so that no two primary units are offline simultaneously, and why water consumption per person is tracked daily and fed into a planning model that projects forward 14 days at minimum. The crew does not feel this system working. That invisibility is the point. The moment the crew feels the water system, something has already failed. Now move to food, because food is where the logistics forecasting becomes its own kind of science. Feeding 5,000 people 3 meals a day means the ship's supply department is running a food service operation larger than most commercial restaurant chains. But unlike a restaurant chain, there is no regional distribution center replenishing the walk-in coolers every 48 hours. What arrives at the carrier during a resupply operation, which itself may be weeks apart and is subject to cancellation by sea state, threat environment, or operational priority, is everything. Nothing more comes until the next event. The planning horizon for food stores on a carrier deployment is not days, it is months. Supply officers are calculating caloric needs by rate and department, projecting consumption curves across a 90-day window, accounting for the increased metabolic demand of flight deck crews who are physically working in high-exertion environments during flight operations, accounting for medical dietary requirements, accounting for the precise ratio of dry stores to refrigerated items to frozen items given the storage capacity of each category. A miscalculation does not result in an inconvenience. It results in protein rationing 6 weeks from land. And this is where the system's philosophy becomes visible. Carriers do not stock for what they expect to need. They stock for what they would need if resupply failed. The margin is built into the calculation, and the margin is protected as a hard floor below which consumption planning will not allow stores to fall. If you were here and you opened the freezer on week 9 of a deployment that was supposed to end on week 8, you would find food. Not abundance, the variety narrows as time extends, but sustenance, because the system anticipated the extension before it happened. This is preventive logistics in its most concentrated form, not reacting to shortage, but structuring the system so that the conditions that produce shortage cannot be reached before a resupply or port call becomes physically available. But this creates a new vulnerability, and it is one that sits beneath every other system on the ship: power. Without power, the desalination units stop. Without power, the refrigeration holds that keep 6 weeks of protein stores at safe temperature begin their climb toward the danger zone within hours. Without power, the medical systems go dark, the navigation systems fail, the communication infrastructure collapses, and 5,000 people are in a steel hull without propulsion in waters where being motionless is measured not in inconvenience, but in threat calculation. The carrier's power architecture was built around a single overriding design principle. There must never be a single point of failure that takes the ship dark. On nuclear carriers, the 2 reactors are housed in separate compartments, run on separate primary loops, and feed separate sets of turbine generators. A problem in Reactor 1 does not propagate to Reactor 2 under normal conditions. The electrical distribution system is divided into independent buses so that a fault on one bus can be isolated without cutting power to the entire ship. Diesel generators sit in readiness as tertiary backup for critical systems, not for propulsion, but for the systems that cannot lose power for even 60 seconds without consequence: emergency lighting, damage control communications, certain medical equipment. The reactors themselves under shutdown conditions still require cooling, which requires pumps, which require power, a fact that the post-Fukushima world understands viscerally and that carrier engineers have understood since the first nuclear surface vessel left the shipyard. The power system is not simply a distribution network. It is a managed hierarchy of priorities, and that hierarchy is written into the physical architecture of the breakers, the bus configurations, and the emergency load shedding protocols that activate automatically when a system anomaly is detected. If you were the electrical officer during a partial bus failure at 2 a.m. while the ship is conducting flight operations, you would not be guessing which systems to protect. The hierarchy would already be made. Your job would be to execute it. Here is what civilian logic collapses against: the idea that a ship this large, this complex, and this isolated can actually maintain the medical capability to handle what its operational environment produces. Flight operations generate injuries at a rate that reflects the nature of the work: jet blast, arresting wire snapback, aviation fuel handling, machinery maintenance in confined spaces, and the cumulative physical toll of sustained sleep deprivation across a crew running on 5 to 6 hours in racks that vibrate with the sound of catapult launches at 6-second intervals. The carrier's medical department is not a sick bay, it is a hospital. It contains operating theaters with full surgical capability, intensive care units, dental facilities, optometry, pharmacy, mental health counseling, physical therapy, a laboratory capable of running blood cultures and pathology, and a blood bank that must maintain viable inventory without the ability to call a regional blood center when stock runs low. The blood bank problem is one of the quieter engineering challenges of carrier medicine. Blood degrades with time, different blood types are needed in different frequencies and rarely predictably, and the only source is the crew itself. The ship runs voluntary donation programs throughout deployment precisely to maintain stock levels within safe operational margins. And the medical department tracks inventory against projected surgical need using historical data from comparable deployments. When the inventory projection crosses a threshold, the donation program increases its tempo. The system does not wait for the shortage, it detects the trajectory toward shortage and adjusts before the line is crossed. This is the same philosophy that governs water planning, food planning, spare parts planning, and aviation fuel management, a forward-looking posture that treats the future state of every critical inventory as a known problem to be solved today, not a surprise to be managed tomorrow. And this is where the pressure intensifies, because aviation fuel is a category that sits at the intersection of the carrier's military mission and its logistics architecture in a way that has no parallel in any other operational context. The carrier is not simply carrying its own fuel. It is a mobile fueling platform for an air wing of 70 to 80 aircraft. Each aircraft requiring specific fuel grades, each sortie burning quantities that accumulate across a flight operations day into totals measured in hundreds of thousands of pounds. The JP5 fuel used by carrier-based aircraft is stored below the waterline in tanks that are designed to be self-sealing against battle damage and to minimize fire risk. But the movement of that fuel from deep storage through the ship's fuel distribution system, up through fuel stations to the flight deck, in and into the aircraft, is a continuous operation that runs in parallel with the flight operations themselves. The logistics of this are staggering in their precision. Fuel moves through a network of pipes and pumps under pressure, and the flow rates, temperatures, and contamination levels are monitored constantly because contaminated fuel introduced into a jet engine at altitude does not produce a warning light, it produces a flame out. The Fuel Management Department tracks not only current inventory, but projected consumption across the scheduled flight operations tempo for the next 7 to 10 days, adjusting for weather delays, aircraft maintenance holds, and mission changes. When the projection shows that current stores will not sustain the planned operational tempo through the next scheduled replenishment, the operations department is notified before the shortfall is reached, and the tempo adjusts. The mission changes. The carrier does not run out of fuel and then adapt. It sees the shortage coming and prevents it from materializing. The same principle governs the supply of something far less dramatic but equally critical: spare parts. An aircraft carrier maintains an inventory of tens of thousands of individual line items. Every component that could be expected to fail across the ship's systems and the air wing's aircraft during a standard deployment, stocked to a calculated depth based on historical failure rates, criticality to mission, and the lead time required to receive a replacement via high-priority logistics channels if the part is not aboard. When a component fails, the maintenance crew pulls the replacement from inventory. When the inventory level of a given part drops below its reorder point, the supply system flags it automatically and triggers either a request for delivery via the next available supply vessel or helicopter transfer, or, if the part is available from another source aboard the carrier, an internal transfer. When a critical part is not in inventory and cannot be obtained before the aircraft needs it, the maintenance department begins a process of cannibalization, carefully and with full documentation, removing the working component from one aircraft to restore another to operational status. then tracking the cannibalized aircraft as a known deficit against the next resupply cycle. Nothing about this is improvised. Every cannibalization event is logged. Its impact on the air wing's operational availability is calculated, and the requirement for the missing part escalates in priority within the supply chain. The carrier is always aware of its own degradation, and always working in advance to prevent that degradation from crossing a threshold that changes what it can do. What this describes, when taken in aggregate, is not a warship that happens to support a large crew. It is a civilization that happens to carry weapons. The design philosophy that prevents resource shortages before they happen on an aircraft carrier is not a military doctrine. It is the logical outcome of absolute isolation applied to absolute complexity, a condition under which there is no tolerance for reactive management, because reactive management requires options. And out here, in water that offers nothing and forgives nothing, the only option is the one you created before you needed it. Every system aboard has been engineered not merely to function, but to be knowable. Its consumption rates, its failure modes, its degradation curves, its dependencies on other systems, so that the humans managing it can see its future state and act on that future state before it arrives. 5,000 people sleep, eat, work, and sometimes break in racks and passageways and spaces that have been designed around the assumption that the ship will always have what they need, because the people managing the ship's systems have already ensured that this is true. But there is one system that sits beneath every other system described here, a system that, if it degrades in a way that cannot be immediately detected, does not produce a shortage of water or food or fuel. It produces a shortage of something far harder to measure and far more dangerous to lose in a confined space of 5,000 people under sustained pressure. That system has not yet been examined here, and what happens when it fails quietly is a question that deserves its own answer.